Okay, I'm going. You hear me?
The broadcast is now starting. All attendees are in listen-only mode.
Hi, Gabe. Hi, Jaden. Hope you guys had a nice Wednesday day. I had a good one. I hope you guys are ready to get, you're excited to learn more about material science. Soap. Soap. What comes to mind? I am teaching I am learning about doctors' practices. So SOAP stands for the what doctors do, their process. SOAP is an acronym for Subjective, Objective, Assessment, and Plan. So that's the format that doctors tend to write their notes in to share with other doctors. Subjective assessment being what they see that might be more, more opinions. Objective is like your vital signs that they're objectively true. Assessment is like what they, kind of like the diagnosis, and the plan is the plan for the future. So, random fact of the day. If you go into a doctor's office, you can ask them about the SOAP note. Well, yeah, that was random. That was just to kill some time to let some other people come and show up. So we're going to go, I cover a lot of material really quickly at the end of the last lesson. How did anyone get their get the print, their 3D models? I know no. Oh man, that's a shame. Yeah, messed up. Okay. Well, Mr. Dubik will get it fixed. I know he will. I guess I haven't been in contact with him, so unless he set anything up with you, I might expect him to either show up at some point through maybe in the later half of this webinar, or I guess we'll see. So material science. Let's just get going, because I think there's a lot of stuff that I'd like to cover. We don't have to get to all of it. And if there's anything that you guys are really interested in, we can dive deeper into that if you like. So just let me know. But otherwise, I don't know if you can see all these tabs I have open, but even once we get through the videos, we've got quite a few images and things that I just pulled up to kind of talk about, to get a better idea of, well, to dig down, to get our hands dirty with like what types of tools material scientists might work with. We learned about the different types of materials. Most materials fall into either these four categories of ceramics, metals, polymers, and composites. Composites being just a mixture of these three. So really, these are the three core materials: ceramics, metals, and polymers. So ceramics, we learned were basically, I think a good way of thinking about it is, was it fired in a kiln? And if it was fired in a kiln, or at some point heated and then cooled to become a hard container of some sort, or hard shape, then that's probably a ceramic. Remember, and it's pretty easy to remember some of these material properties because you're pretty familiar with them, as long as you can connect them with pottery, a lot of coffee mugs, bakeware, like serving dishes, that sort of thing. they're all ceramics. Fine china is a ceramic. You know, let's see. So then we talked about metals. You think about where metals used, the copper wires, and just wires in general, because they're strong and have a high electrical conductivity. We mentioned the tension, the suspension bridges. Metals are really good at under tension, as well. In wires, the electrical conductivity, also thermal conductivity. Think about heat sinks in your computer, or just a heat sink in general, or a radiator. A radiator has a lot of surface area, so that because it conducts heat really quickly, so the heat spreads throughout the whole radiator very quickly, and the more surface area it has, the faster it can conduct that heat into the air. And the same is true with a heat sink in your computer. It's going to be it's going to connect to to the hot part, usually the processor. Sometimes other things like your graphics card, if you have a powerful graphics card, they might be connected to a heat sink. And sometimes there's even a fan to help that air circulate. You can hear when your processor starts doing a lot of work. Well, the processor is not perfect, so those electrons flying around in the processor kind of end up bumping around and on their way to where they're going in your computer, and that causes things to heat up. So that's an example of where the metals, a metal heat sink would be really useful, because if things heat up too much, well, your processor is made out of materials, and your computer is made out of materials. Like I know my computer is made out of plastic. It's a pretty hard plastic, but if it got too hot, it would melt. And I'll show you some examples of how plastic melts in a little bit. But also, the computer chip itself it's got lots and lots of layers to it, and they're so fine that if those layers get messed up in any way, the processor heats up too much. It'll overheat, and some part of it will fail. Either the thin copper wires might melt, or something will happen that's bad. Usually some kind of melting or material failure. So you have to really design, the material scientists would be involved in designing that heat sink so that it can remove enough heat, fast enough to not overheat the processor and that sort of thing. All right, they're also generally malleable and ductile. Malleable means fairly flexible, bendable. Ductile is a similar word. I can't remember the difference off the top of my head between ductile and malleable mean. I might come back to that and Google it in a sec. Let's see. And metals are often made up, or there's the pure metals: iron, copper, gold, silver, tin, and then you've got alloys that are made up of some components of the elements. For example, steel. I'm trying to think of some others, but I'm just drawing a blank. So you guys could probably think of some if you just named metals that you thought of off the top of your head. Any ideas? What other metals? We use more metals than this. How about this list of metals? Ooh, list of alloys. There's a good one. Okay, well, lithium is an alloy. Nickel and oh no, that's never mind. Not an alloy. It's bad. I just read really quickly. Lithium is definitely just an element. Chrome is an alloy. It's mixed with hydrogen. is nickel, or contains nickel and chromium. Let's see some other examples. Brass, that's a common one. Brass was one of the early metals formed with zinc and copper. Bronze is another one. Usually, it's either formed with copper and tin or aluminum. They didn't have aluminum until recently, we learned, so it actually was formed by tin back in the day, in the Bronze Age, when they discovered how to mix tin and copper. And there's other examples. You can look them up if you like, but I was trying to think of some of those ones that you think of because of the age that they were from. All right, and so polymers. Then we got into some examples of what is a polymer? Well, a mer is one unit, and you can think of that one unit being one molecule. With specifically to be a polymer, it has to have two active sites. So those active sites are the same as two bonding sites. So if you were if you were a monomer that could become a polymer, you had the two active sites. You could grab hands with two other people, and they could grab hands and continue linking, and grow that way. So they become really long chains. They get twisted up with other chains of the same type usually, and so they end up with tons of repeating units. And they just repeat for so long. But there's so many different types of polymers that's really a broad classification. You can make anything from PVC pipes. Wool is a polymer. Rubber and nylon, also polymers. Nylon actually is an experiment that you can do. I'm not sure if you can do it at home. I can't remember what materials are involved, but I think one of them's slightly poisonous, but or toxic, maybe not poisonous, but I definitely remember seeing someone do a science experiment. You could look up at YouTube. Nylon's a pretty cool one. Then, no, Gabe, I have not ever mixed large amounts of styrofoam and gasoline. What happens? Composite materials, we talked about, it's just made up of two or more different materials. They usually blend the characteristics of the materials involved. Sometimes they're just different, but usually it's more of an average, and sometimes it's a slightly better than average in two different, if you're looking at several different fields or several different example or materials, you might get a better material out of the composite or better performance out of the composite material. So apparently, Gabe says if you mix large amounts of styrofoam and gasoline, you get napalm, which, as we know, is a really toxic, also very flammable substance. Let's see. Used in World War II, I think, to make, I think in the bombs that they dropped on Japan to help Vietnam. That's right, the Vietnam War, to drop on to help clear the forest, and also, yeah. So it burned down the forests. Also, it led to lots of cancer, and the fumes and the materials created when napalm burns is super, super toxic. There are a lot of misformed pregnancies. Babies had lots of malformations because of the chemicals in napalm. So yeah, definitely not something you want to ever do at home. Let's see. Okay, so some common composites. we really breezed through this last time, so I'm going to start slowing down a bit. Concrete, we did cover that. How concrete is poured, but it's a mix of kind of the cement, which is different from concrete. Cement is if you were to mix just water and let's see, if you just mix water and Portland cement, you get cement, like hard cement. But if you add in rocks or steel rebar, you turn it into a composite where it's more than just aggregate. Is also just rocks. It's the same. It's just the industrial term for rocks or other chunks of material. And so rocks are generally pretty strong. They're not going to just crack on you easily, especially in a cement. And so they add strength to it. Whereas Portland cement, if you didn't have the rocks in there, it'd be easy to chip and that sort of thing. But rocks are pretty resistant to chipping, so that helps hold the cement together and make a stronger cement. The Portland cement is actually much better, performs much better when it's very thin. So having those rocks in there and sand as well. So they're kind of like filler materials that the Portland cement is really good at bonding to connect the sand or to form around bits of sand and bits of rocks, and all of that together creates the whole composite, which is a much stronger structure than any of the three combined, or can be, and moldable, I guess, more moldable than any of the rest as well. So wood is also a composite made of cells. Cells aren't just one molecule. Cells are a lot of different materials all in one. And then they contain the glue called lignin. That's the molecule that bonds, or the molecules that bond the cells together, hold them together. And so you can think of wood as also a composite material just because of the huge variety of structures and chemicals involved. And then tires are usually, so the way tires work is they kind of layer rubber with fiber, so that the fibers are long, stringy, and good, and really good under tension, kind of like steel. They can be steel fibers. Sometimes they might be. There's a huge variety of ways to make tires, but we can just think of them as being steel fibers or nylon fibers, something like that, that are wound around, and then layers of rubber and layers of fiber, so that when there's a lot of pressure, the rubber is airtight, so it maintains the pressure inside the air inside the tire. But while the tire is rolling along, the fibers absorb most of the impact, so that the rubber, which without the fibers would just deteriorate very quickly, it really holds the rubber together a lot more. So another example of composites being stronger and having features simply, you kind of often pick the best of both worlds when you mix composites. Now, it's important to mention, though, that these fibers would be stronger if they weren't mixed in like this. This concrete, these rocks generally, they keep the properties of some of they often blend the properties. Like if you put rebar in concrete, well, the rebar, the metal that you put in there, is really good under tension. So you add to the ability of the concrete to absorb tension forces. but you do, in a small amount, reduce. But you could absorb more tension with just the rebar itself. Whereas, the concrete's really good at compressive forces, but with the rebar inside, it might be a little weaker, maybe, but you really are going for the combination of both. That's why you do it. And then glass, it's different because it doesn't quite fit into our ceramics, metals, polymers, composite structures, so it's still just one chemical. It's not a chain, but it has a state that I'm not sure if you've heard of or ever seen really old windows. Like it may be in some really old houses in the U.S. Some of the earliest houses, their glass that they used was, if it's still in the building, some glass has survived that long. You can actually see how the glass is fatter at the bottom than at the top, and that's because glass is actually still a liquid, but it's a liquid that moves so slowly that it retains its it looks like a solid and acts like a solid. Now we've seen how glass recently has really changed in how we saw a video last time about how the drastic change in how glass reacted. There's another video on glass from Corning. The first one was from MythBusters, but we'll go ahead and see. That's part 2. Here we go. We'll go ahead and watch this video, and then go back to materials. All right.
Let's switch gears. Your smartphone. You hold it in your hand, you put it to your ear, you keep it in your pocket or your purse. It's a great everyday use of glass that you might not think about.
Until it breaks.
Until it breaks. I myself have shattered over a dozen of these, but you might have noticed over the years that the display on your phone has been getting harder to break. Let's go back a few years. If you'd done that to your standard 2008 phone, that's what would have happened.
Not pretty.
No, and that could easily happen just by keeping your keys and your phone in the same pocket. And if you then dropped that phone, well, the probability of the phone breaking was high.
How high?
Very high. Let me show you.
Aren't you going to drop the phone?
Well, sort of. Instead of dropping the phone, I'm going to drop something on the phone, this steel ball.
For consistency's sake.
Exactly. In this way, my phone drops exactly the same way every single time. Here we go. 3, 2, 1. Oh.
I've seen you do that so many times in real life.
Me too. But that was then. This is now, thanks to Corning, we have Gorilla Glass.
I'm pretty sure that's what I've got on my phone.
And it's on this phone as well. I'm about to do the same test a second time. Check this out.
No scratch.
Not at all. Now, same drop test. Ready?
Yeah.
3, 2, 1.
Wow.
I don't know if you could read the text there, but it just said that the impact that they tested was equivalent to a 1 meter or about 3 feet drop.
What a difference a few years can make.
Actually, Corning came up with this method for strengthening glass long ago. Gorilla Glass evolved from that process, and today is found on all the best small devices, like this. It's beginning to find its way onto larger format displays, too. Now, it's not unbreakable. If you set out to break it, you will. But as Corning figures out ways to unlock more secrets of glass, it will continue to get more resilient. It may even get to a state where devices such as these...
Oh, he already showed you this. Okay. Well, I just sent you the link. Thanks for letting me know. Yeah, are you sure about this? Because we saw an earlier another MythBusters video. Part 1, not part 2. Okay. Yeah, I thought so. Yeah, this is a continuation of the Gorilla Glass. Okay, I'll keep playing.
Simply don't break anymore. Oh, and by the way, Corning has just come out with a new and improved version of Gorilla Glass.
Really?
Yeah. Let's go deeper. Watch this.
Odd stuff.
Yeah, this hot stuff is your basic everyday soda lime glass. There's nothing remarkable about it except that it's white hot and molten. There we go, and I'm going to drop it in cold water. It's called a Prince Rupert drop.
Who's Prince Rupert?
Some Bavarian from the 1600s. He came up with this. Okay, so there's a few things going on here. The cold water rapidly cools the exterior surface of the glass, hardening it almost immediately. The interior, still molten, cools more slowly. As it cools, it contracts and attempts to pull the surface in with it, but it can't. Well, not very much. The surface is already hardened, so it gets pulled in only a little, compressing it while also creating an internal layer that remains forever under tension. It is this action that gives the glass its uncharacteristic strength. We call it compressive strength.
It sounds like the same principle as how an arch provides strength in structural engineering.
Yes, kind of. Now, Jamie, I'm going to ask for your help. We're going to attempt to destroy this Prince Rupert drop. I just want you to tip that hammer past its center point. Go ahead.
I feel like we've been swindled.
Swindled not. We have just experienced the power of compressive strength. It does, however, have an Achilles heel. Take those nippers right there and nip the backside of the tail of this Prince Rupert drop and watch what happens. Wait. Cue the high-speed camera. Okay, here we go. Oh! That was even cooler than I thought it would be.
You guys want to see that again?
That... Oh! Prince Rupert drop and watch what happens. Wait. Cue the high-speed camera. Okay, here we go. Oh! That was even cooler than I thought it would be. That is what happens when you release the stress in compressive strength glass. The whole thing shatters.
Spectacularly.
Yes, well, at least in that example it was. That's because the stress was so great between the outer compressive layer and the inner tension layer.
That when released, it was a catastrophic result.
This
That's right,
is
Gabe,
Gorilla Glass. It has been refined over time, but like all Gorilla Glass variants that came before it, it is compressive strength glass. But it's not made in the same way as we just demonstrated, the rapid cooling method. No, instead, Corning uses an ion exchange process. To break it down simply, the surface ion particles that naturally form during the manufacture are replaced with larger ion particles. Once exchanged, the larger ion particles create the same sort of inward pressure that we see on the Prince Rupert drop. And with this method, they are able to control and manage the resulting tension.
I think what you're saying with this process is that they're able to tune strength in the glass by dialing in the right balance between compression and tension?
Yeah, that's a great way of saying it. That, and also by adding in a few other tricks that change the molecular structure of the glass. Corning is steadily moving forward towards the Holy Grail.
Thin, unbreakable glass for our mobile devices?
Well, maybe not unbreakable, but yes, thin and very tough. And by the way, the applications for this tough glass go well beyond mobile devices. Let's go over this one. Behold, the common automobile windshield made from regular soda lime glass. It's quite strong because it's very thick and it's laminated, which means it's two pieces of glass bonded together using resin in the middle. And the resin does two things. It gives it added strength, and it holds the glass together on impact. You've probably seen.
So what he's talking about right there, two pieces of glass with resin in the middle, that turns that into a composite material, which, as he's just about to say, it makes something, have similar, gain properties of both, right?
Broken windshields before. Lots of crazy cracked glass, but still mostly held together in the shape of a windshield.
Like this. That's pretty cool.
Yes, it is.
So that resin is stronger than, is strong enough to hold the glass together during that impact. So when you hit it with the hammer like that, both sheets of glass crack, but the resin actually holds it together, and that's why. That was a huge improvement in automobile windshields, because before that, they bust, which is really bad. Obviously, glass goes everywhere, and that's just causes more problems. So, let's keep watching.
Windshields have been made of laminated glass for the last 100 years, and they've served us well. But there is a big drawback.
I think I know what you're going to say. It's heavy.
Yes, very heavy. And as we strive for more energy-efficient cars and trucks, the weight of all that glass can be a bit of a problem.
I have a feeling you're about to show an alternative.
Yes. Take a look at this. Now, this is also a laminate windshield, but it's not one you find in production. It's experimental, which is great because we're going to experiment with it. It has regular soda lime glass on its outside surface and resin in the center like the other one, but this windshield has Gorilla Glass on the inside surface.
Sweet. It looks thinner.
Yes, it is. And a lot lighter, too. In fact, just by changing the one laminate, the overall weight is reduced by about a third. In a car, that adds up fast.
Thinner, lighter, and let me guess, it's just as strong as windshield A.
Well, maybe. Let's find out.
Oh, goody.
Okay, wait, no. You don't need the sledgehammer for this one. Put that down. Instead, you're going to shoot this windshield with an air cannon.
Cool.
No, don't get too excited. We're going to have to mount this, tie it down so it doesn't wobble, and we're going to simulate a pebble hitting this windshield at a super high speed.
Good enough for me. When do I start shooting?
Well, before we shoot the Gorilla Glass laminate, let's shoot the regular soda lime laminate, windshield A. This way. All right, here we go. Perfect. You want to do the honors?
Sure.
I'll count it in. 3, 2, 1, go.
Whoa.
That was a lot of damage.
Can we see that in slow motion?
The ball bearing hits the windshield at around 120 miles per hour. This could be a stone flicked up by another car. It penetrates the exterior glass, it stretches the resin, it's slowed down a bit, but it still has momentum to break the interior glass layer, causing small fragments of glass to spray out through the interior of the car.
Not good.
So let's try windshield B. The Gorilla Glass didn't appear to break. The foil is intact.
Let's see it in slow-mo.
The ball bearing hits the windshield at around 120 miles per hour just as before. It goes through the front layer of soda lime glass, stretches the resin, but doesn't have enough energy to break the Gorilla Glass. It's not bulletproof. I'm pretty sure if we turned up the velocity, we'd breach the Gorilla layer too. But in this test, and all things being equal, it performed a lot better than the thicker, heavier soda lime laminate windshield. That's impressive. What we're seeing here is compressive strength at its finest moment.
Okay, so it's lighter, thinner, and stronger? That's pretty good.
Yes, it is.
Can I get this on my car?
Not today, but soon, I hope. Come on, though. After living through the Iron Age and the Bronze Age, you can wait a little longer. Actually, when you think about it, the application for this goes way beyond the car, doesn't it? Ah, yes. Feels good to be in the glass age.
Don't touch me. Sorry.
All right, so that was cool. Yeah, I don't think I have anything to add to glass. Those are the Mythbusters. What you're thinking of, Gabe, is it's two guys. I'll think of it. It'll come to me in a sec. All right, so yeah, that's everything about glass. And that's the end of the slide. So a quick mid-lesson detour. Previously, you guys asked about how to put, use this code in a web page. I mean, make it online so that I could send this to you. You could send me the link, and it would just show up on my computer. That kind of thing. Sharing, your actual site that you created. Well, you can actually do this on Google Sites, and I just hadn't explored this until last time. So if you go to your Google site and you go to Insert, and then you go into here, HTML box, then you paste your HTML in straight from there, and that's then it shows up just like you expect. Last time I just tried pasting it in here, and that didn't work. So I'm going to go ahead and send you the link to the how-to right here. And so you can put more than just HTML in there. We didn't cover how to put CSS and JavaScript directly into the HTML. We've always had 3 separate files. Well, in Google, you have to put all of those files. You have to put them all in the same HTML document. But that's not hard to do, and I would suggest we just don't have time to go over it in class. So I would suggest just Googling how to insert or how to put CSS in the HTML file, how to put your JavaScript into the HTML file. They do mention down here, though, that they will that you can put the jQuery external JavaScript file. So if you click on this link, it'll tell you in that link that I sent you, it tells you how to include that. That link to the jQuery is considered an external JavaScript file. So anyways, that's how you do that. So while not entirely material science, this goes back to chemical engineering a little bit. But I want to talk about, I mentioned previously, in many lectures ago about the Haber process and what that did and how it changed our society. So I wanted to talk about that and kind of relate it back to material science a little bit. So this is Fritz Haber in 1918. He was the mastermind behind the Haber process, and so he developed this during the war. They needed to create a lot more, create nitrogen a lot more cheaply. Previously, they had to extract nitrogen from rocks. They had to mine nitrogen. The nitrogen's all over us in the air. It's actually 70% of the air is nitrogen. So, but it's in a form that's really, really difficult to use. Nitrogen's really stable. It's N2. So, but he discovered that if you add, let's see, so the process combines nitrogen from the air with hydrogen derived mainly from natural gas, which is methane, into ammonia. And then ammonia is a molecule that you can do a lot of things with chemically. It's really flexible. And so that they created this reaction, this way to combine, take nitrogen from the air and turn it into ammonia. Now, this slide just briefly shows how they do it. And the big thing that he used was some properties of chemistry, or some things that they've been discovering about chemistry, where really high pressures and high temperatures really affect a lot of the chemical reactions. If you go all the way up to 200 atmospheres and 400 to 450 degrees Celsius, in the presence of an iron catalyst, then you can take the nitrogen and the hydrogen, mix them together in this really high pressure environment, and then as the gas is cooled, ammonia is created as a gas, and then you cool that gas, and then the ammonia turns into a liquid. So that's the process. Now, the impact that actually had on our society was that now that we were able to take all of this nitrogen out of the air rather than mine it, nitrogen was at that time the single limiting factor for food production and crops. So after the war was over, after they finished making their bombs out of nitrogen was involved in a lot of bombs, and that was the incentive for the Germans developing that. But after that, what really kicked off the growth of humans and actually kept us on the accelerating growth curve was the fact that we learned how to make fertilizer with these nitrogens, and the plants that use the nitrogen. That was the limiting source of nutrient. So that because the plants couldn't find enough nitrogen in the soil, that was what was limiting their growth. So once we figured out how to capture that nitrogen and give it to plants in the form of fertilizer, then our food production just went off the charts, and really in the amount of food that you could produce on a single acre, it more than tripled. It might have even done something like 10 times. I don't know off the top of my head, but you could produce somewhere between like 3 and 10 times as much food on the same plot of land when you add the nitrogen fertilizer. And that came with negative consequences too. Nitrogen fertilizer is not, or a lot of fertilizers aren't necessarily great for the environment, especially when the fertilizers aren't absorbed by the plants, but are washed away by the rain and that sort of thing, and get into the lakes in our water system. So, and we're still dealing with those effects today. But we wouldn't have 7 billion people on the planet if this paper process weren't invented, and we didn't know how to take nitrogen out of the air. So that was more of so we knew that nitrogen was really important to plants before that. That's like we know how to do something, and even when we discovered this Haber process, it wasn't immediately, it wasn't overnight. It took a lot of time for this to come through. So that's one of the things with this new technology, is that it's not immediate. He mentioned in the video, the Mythbusters did, that Corning had understood this properties of this Gorilla Glass. They kind of had the ideas behind it, or understood how to make stronger glass, but they didn't know how to do it fast and how to manufacture it up to scale where they could mass produce it for tons and tons and tons of smartphones. So it wasn't cheap, and it's still not cheap, but it's cheaper than it was. So it's kind of, this was just another example of how it took, this invention was invented, and then it took a while, a little bit of time, and then you saw the accelerated growth it had on humanity. To be very broad about it, but anyways, so let's go back to a little bit more specific, very material properties. So when you stretch a material, these are mechanical properties of materials. So mechanical engineers, material engineers, all deal with this sort of thing. If you take any engineering course in college, you're likely to see this sort of diagram. So what they're plotting is stress versus strain on the plot. You could ignore a lot of this terminology, and we're going to have a lot of terminology in these charts that I just want you to ignore unless it doesn't overwhelm you, because these are just charts I found on Google that really have a lot more than I don't even understand necessarily. So the stress versus strain, this plot can tell you quite a bit about a material, and so it's one of an important tool in understanding how a material behaves and in selecting a material for a certain application. So what this is showing you here is the strain is how much force you're putting on. No, sorry. The stress is how much force you're applying, and the strain is how much. Oh no, I might be getting this backwards. Let's see. This is the point of rupture. So, oh, I'm just going to Google this because I don't want to tell you the wrong thing. Okay. Let's go to Wikipedia. All right. Let's see. Stress. Okay. This is the strain is caused by the stress. The stress is applied by the external force, and the strain is inside the material, like the internal resistance and the internal forces in the material. So let's go back to here. So the stress is like how much you have to push on this material. So as that goes up, this material bends under strain. So you can measure that on a graph. You usually measure strain by like how much the material changes in length. So if the material was originally 20 centimeters long, and under strain it bent, it bent by 1 centimeter, then strain is that ratio, 1/10, so 0.1. So what you can get out of this is, what you can understand from this is, as long as this is straight, then you're getting an equal absorption of force for the amount that you put into it. But at this point right here, what's called the yield point, then that is when the material starts to actually, you're no longer just stressing the material, but it's actually causing things to break or things to bend more easily, I guess. And then there's often a point where the material can hold more stress, but it's actually permanently deforming, or deforming a lot more. And then there's the point where it ruptures, where once it's this top here is the ultimate strength, because once you give it more stress than this ultimate strength point up here at the top, then the material, you can imagine as soon as you pass this ultimate strength, if you apply a force higher than the ultimate strength, well then immediately, because this, let's see, so it's saying the actual rupture strength is up here. So like if you apply a force this high, then this material is going to bend, and then bend more and more and more, because it's actually getting weaker. But as long as this is going up, the material is still getting stronger. But once you get to the top, that's the ultimate strength. So I made a mistake. It can actually return back to its original, once it gets to here, it will return back to its original shape, because you're not affecting the properties. Now, once you get it to here, it'll bend and it'll actually break, but it's still strong. So it might return back, I don't know, to a different point on the graph. But that's not what I wanted to get into. It gets really complicated really quickly. Now, yeah, that's exactly it, Jaden. Look at diagram and then go blah, blah, blah. So I'm going to try to make this clearer because it really illustrates a lot of things. So I'll try to give an example, different examples, and maybe that will help you imagine what this is. So if you can think of a brittle material, right, the ceramics, glass, not the fancy glasses that we saw by Corning, but just standard glass. So if you can imagine, I imagine a piece of fine china especially, yeah, glass is a good one. So when you put stress on glass, when you try to bend glass, what happens? You can barely see it bend, if at all. So that means, as you apply more and more and more and more and more force, I hope you guys can see my mouse. Can you? I'm trying to illustrate things with my mouse too. Anyone? Can you actually see my mouse when I move it around? Yes. Okay, good. So when you apply more and more and more force, that glass is not straining. It's not bending under that pressure. So until that point where it just breaks. It can't take any more stress. It can't take any more stress, and the internal forces are too great, and then all of a sudden it shatters. That's a brittle material. So there's no what they call plastic deformation, and you can think of plastics and metals as plastic deformation. So here, another example is a strong material that's not ductile, like steel wires. They're similar. They still stretch a little. So rather than having such a steep curve that this glass is barely bending at all before it breaks, this steel wire, they stretch a little, but not very much, and then all of a sudden they just break. Well, ductile materials, I'll explain what happens in that. Let's see. So let me try to think of an example of a ductile material that might exhibit this behavior. Like, well, I'll just explain it first, and then we can look at examples. So ductile material will bend and bend. So think of coming on this strain. It's really just more and more and more bending. But it's how does it bend? So does it, like when you apply stress, when you apply the same amount of stress, how much more does it bend? So a ductile material will bend and bend and bend, like steel columns, and they're usually fairly ductile. They'll bend and bend and bend, and then, and actually this is why often metal steel supports are used in buildings, because they are ductile and they have this extra, like they will give, but they're still strong while they give. Give being bending under pressure. So the stress is being applied, and then there's this weird section where it's called necking occurs, and then once you reach here, this bending is permanent, but it's called plastic deformation because it's not. It actually, it goes through this quickly, but because of the material, it still holds together even though it's bent. And so, this is the big improvement over something like wood beams in buildings. They're really strong, but you can only build a building so tall with wooden beams because skyscrapers undergo huge pressures. Even just many level buildings, they undergo huge pressures. So if any cracking they're more of these brittle materials where, once it starts cracking, it'll break. It could break pretty quickly. But whereas steel, and the building would collapse. If it breaks really quickly, the building is going to collapse, right? So steel, once it reaches these peaks, it actually continues to get stronger even though it's bending. And that's something that we can detect and know, okay, this building is permanently deformed. These steel beams, you can see them bent, but it's the buildings hanging together. And that allows people to escape and get out of buildings. It also allows you to build taller buildings safer. And so that's a really important property. And then there's plastics where you can think of like silly putty or other plastics where you bend them, even just the plastics, Tupperware and plastic cups. You bend them a little bit and they have a little bit of strength, but then once you start bending it a little bit, it gets really easy to bend. But it continues for a while. Like you can keep bending it, and it holds together, but it doesn't break. So Tupperware is a really good one to think of, or plastic cups, and that sort of thing. Where not the brittle plastic cups that just snap, but the softer plastic that doesn't snap. So then, now if you think about these stress diagrams connected, as muscles, you can measure stress and strain for any material. So for muscles, they have a region here that's this diagram looks pretty similar. Here's the linear region where you're not breaking anything, except actually you are technically as you work out. So when you work out, that working out does break muscles as you use them. That's why you get fatigue when you work out. So you are breaking muscles, but that's on the microscopic level. You're getting microscopic failure, and when you break muscles, that's part of the body's natural process. They heal back stronger, and that's how you continue to get stronger and stronger, is to use your muscles in this region right here, this linear region. But then as you apply more stress to the muscle, if you pick up a weight that you can't carry, or say you're trying to hold a force, and maybe you're underneath a car, and I know there's that image of someone can you probably all heard of the really crazy, someone lifting a car and actually escaping, but it's just a one-time thing. Like they've actually ruptured their muscles. Yeah, so like if you hold something heavier than you can carry, or if you've worn these muscles down enough, then you get macroscopic failure, and then you get problems like your muscle actually tears, and you have to have surgery to repair it. So you can analyze the body in these terms too, and that's biologists even use these stress strain curves to understand how the materials in the body behave under stress and that sort of thing. Now, one thing to think about is that as you're working these muscles, it does your macroscopic failure, your rupture point gets lower and lower and lower each time. You're in the body and you're breaking muscles this whole time. So every time you break some of these microscopic muscles, little muscle fibers, you're getting weaker because there's fewer of the fibers connected. So you might start off with your workout with your muscles having this rupture point up here, but you might end with a rupture point down here, because they're actually weaker because you've actually broken some of those fibers until they grow back in the next couple of days. So it's 7 o'clock, and this is a good stopping point. So, sorry, 8 o'clock. It's 7 o'clock here, but 8 o'clock where you guys are. All right, so you guys have a good night. That's all I have for you. Next up, if you guys want, we'll continue. I've got maybe 15 more minutes of material science for next time, but otherwise we'll be moving into Unity. All right, have a good night.